And welcome to Ascendo Reliability's webinar today. This is Fred Schenkelberg. We're going to talk about one of my favorite topics, accelerated life testing. And as I was putting this presentation together, I started, I just was curious, how many times have I talked about this in the last 5, almost 6 years? And it's 3 or 4 different webinars now, fundamentals of and basics of, and 6 different approaches or 6 different methods, I think was one of them. Um, in the recording page, I'll put the links to some of those. And welcome, Long Jun. Good to see you again. And welcome to everybody else that's joined us for the live version of this. And as usual, as many you already know, we'll be using the chat window, and I expect to interact and see your questions and comments and address those as we go, and hopefully spark a few ideas around one of, like I said, my favorite topic. And for those that don't know, I actually got started in reliability engineering, unbeknownst to me that it was called that at the time, when my boss came in and said, "Hey, could you figure out how long this will last in the field?" And we're hoping it would have a low probability of failure out to 20 years. So I kind of got dropped into the deep end of accelerated testing because they wanted answers in 6 months. And so that got me interested in both the statistics and in the how things fail. And it just has led to a lot of fun and hopefully a lot of value added as I went through my career. And still do. I still get questions about ALT on a regular basis. So it's usually top of mind for me. All right, let's see if I can advance slides. So one of the things that we get asked and or we ask is, when's this thing not going to be working anymore? Now, this implies that we know what a failure is, and hopefully this person on the natural bridge here uh, is confident that that's enough rock there that they can safely traverse it and hopefully then get back. But it's one of those things that we know that, and many of the engineering and managers that we work with and our customers also, we all realize uh, that things fail. Everything's going to fail at some point. And the real question that we have is well, when? And if we're in a product development case or in a product development or a factory setting, if we know when something will fail, uh, we can either design it so it'll last longer or do maintenance so that it'll extend its life and avoid the costly parts of failures to as much of an extent as we possibly can. And so this question of when something fails is really common. And we also hear it asked in a different way is, will this last long enough? And so, will it go through the shift? Will it go through the run? Will it survive through the warranty period? And so, we typically connect this probability of failure with time. And so, I have a hard time, as I believe all of you know, with just saying I have a failure rate or a MTBF value, because it doesn't also include over what duration. Now, if I give you a, 3 ppm per hour or a failure rate per year, well, how many years or which year? Because it matters. If we want this bridge to last 150 years, knowing that it will work for 1 hour at a very low failure rate really doesn't help me a whole lot unless we know over which set of hours the assertion applies. And so we often get asked this question, and it's usually in context, will this last for its mission, for its during the entire run of this product in our factories, or will it run long enough that the customer's happy with the product and that they're satisfied with that product and they get their value from it. And so that's one condition that we have. The other issue of this, which brings up the need to do accelerated testing, is that we need to know the answer sooner than later. Now, back to my original story, my very first question back to my manager when he asked me to figure out how long this new product would work, um, was, oh, well, I'll just go to where it's being used and monitor it for the 20 years. And well, I was happy to do that because it was going to be in northern Italy in the mountains, and I do like being in the mountains. And he goes, no, 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 we need an answer in 6 months so that the customer will be confident in our ability to design and manufacture a product that will actually last for 20 years with a very low probability of failure. And I said, oh, okay, bummer. Well, can I at least go to Italy to see where it's used? And he says, no, it's going to be buried in concrete. We got concrete here. And so that was the quick start of my reliability engineering career. And then later went off and did a bunch of testing to understand the degradation pattern of this particular material, this system that we were building. So that was a lot of fun. So let me pause for a second and get a sip of water and open up the chat window. Or are you currently doing accelerated testing? Do you have something going on, or do you have plans to do one, or is it something that you haven't started yet? What's your status related to ALT or accelerated life testing? Yes, regularly. Thanks, Sebastian. All right, we're doing halt. Okay, yep, routinely. Good. Thanks, Mark. All right, there's a few more of you out there. All right, I wish we did halt. That's a good one. Thanks, Sean. Halt and alt. Good. David, thanks. All right, now today I'm not really going to talk about halt, highly accelerated life testing, which, by the way, I think is our second worst four-letter acronym. Um, and it's Well, I probably should do a whole nother webinar on why I think that. But the idea is that it really accelerates and it uses many of the same principles that we talk about when we apply stresses um, to a product in order to increase the probability or the rate of occurrence or the chance of occurrence of a failure mechanism. And while it applies some of those same principles, we often use multiple stresses in order to excite as many different failure mechanisms as we can. And there's some other subtle differences with regular ALT, which I won't really go into too much. And Brian, I noticed, thanks for your note here, is this is one of the things I think is common. ALT is expensive. And so if and when you do one, it should be for some purpose. It should actually provide necessary information so somebody can make a decision. And that very first project I did, it was very clear right from when I received the task that the answer needed to be sufficient to communicate, did this product last for 20 years or not? And what was the expected probability of surviving that 20-year period? And we knew that it wouldn't be zero, and we also knew it wouldn't be one, that all would survive. But they needed to know what proportion would be expected to survive. And that was in order for this customer to make a decision to buy the product and install it or not. And it was for our design team to understand if it was going to meet their targets or not. And so they may have a chance to make improvements. So the idea of doing ALT in that particular case was to create a piece of information that informed a major purchase of a product for a relatively large project. It was going to be going into uh, road beds on bridges in the northern Italy alpine area. And so the idea was is to when it got to the right conditions and snowing or raining to heat the bridge up so that it wouldn't form ice. And it was a major cause of accidents for them and fatalities of people hitting the ice on bridges and crashing. And so they thought, well, if we can melt it before it forms or keep it from forming, we can have nice, dry, clean, easy to drive on bridges. And it turned out years later, I was up there and in the winter, we were going skiing and the bridges were dry. The roads were ice packed and not necessarily treacherous, but there was ice and snow on the roads, but the bridges were dry and clear concrete. So that I was very happy to see that and suspected that it had to do with the product that we installed. And it was in part due to an accelerated test result that gave them information that allowed them to make a decision. So that was pretty cool. Now, I don't know that I found any bridge um, images that are of those bridges in Italy. There might be one or two that would be similar to what I saw there. But let me talk a little bit about this accelerated testing idea in some of the issues that we have when we go about setting up one of these tests. Now, the basic idea is that let's say that I keep going back to this bridge in Italy. It's in the mountains, so it's got some altitude. It's going to be buried in concrete, right? So it's not going to be easy to maintain or repair or replace. It's got to work. And we did an extensive amount of work on making sure it was compatible with the process of being tied to rebar and buried in concrete and during that entire cooling process and then the freeze thaw cycles and thermal cycling type of the concrete itself and just the rough nature of it and all those kind of things. And we also looked at, well, what are the chemicals that are inside concrete and the materials that are there and the rough aggregate and edges and stuff. And so we did a number of different tests that were related to the expected stresses, environmental stresses and use stresses that would be applied when the product would be in use. For accelerated conditions, we increase those stresses. So I remember one of the engineers, she was concerned about shovels and moving concrete around when it gets poured. And the workmen or the crew would be pouring concrete and using spade shovels oftentimes to move it to where they wanted it to be to create the slab that they were forming. And one of the thoughts was, well, if you jam a shovel through concrete, they're used to hitting the rebar and it's a piece of metal. And this is a blade, basically, shovel, and with quite a bit of force. So the question was, well, how much force is that? And so she went off and measured how much damage, how much cut through could a shovel being thrust into concrete do to our product. And so part of the design is based on her research was how thick the coating needed to be in order to withstand being cut through and shorting the electrical uh, elements of this heater. And so one of the stresses was, how hard could somebody hit it? And so she measured what would be typical and then kind of, I think she actually doubled or tripled it in order to create some margin in case somebody really stepped on it or pushed it exceedingly hard or multiple times. Yet she didn't use unreasonable force. And by that, I mean, she didn't use forces caused by, say, a large pneumatic hammer that could create 47 tons of force across our product. Um, the risk was of the crew using shovels causing damage to the product. It wasn't some laboratory mechanical chopping machine. uh, causing the problem. So we went within a reasonable range. Same with temperature. Now we formed the coating or the jacket for these products in an extruder, and it was commonly like 300 degrees Celsius would be the melting point for these engineered polymers that we were using. To some of them were that high, others weren't quite that high. This one was pretty high, and but we didn't test it to 800 degrees Celsius because they would just melt it. Didn't make any sense. So we looked through our material set and looked at where the phase changes would be. Now, since this thing was going to be used outdoors essentially and buried in concrete, um, we don't have water as an integral part of the product. We didn't pay much attention to the 0 and 100 degrees C because those were phase changes for water. And the material sets we had a much wider range before they ran into the phase changes. And so we uh, went forward with the set of stresses that we're applying. And for my particular tests, because it was a duration over the 20-year period, the most likely long-term failure rate would be a degradation of the material, of the polymers itself, which is one of the features of this heating system that we're working on. And it would oxidize. And so it was a chemical process, and we went straight to Arrhenius equation, and we used temperatures that didn't get too close to the melting points because the polymers we're using were not eutectic, meaning that they transition exactly at their transition temperature. Polymers have various different lengths and sizes of the polymer chains, and so they soften well below their melting point. And so we stayed way below that. Yet we wanted to get high enough stress that we would get results within the 6 months that we were looking for. So it was that reasonable range that caused us to say, well, I could go up to the melt point, but that will give us a phase change with some proportion of this product. So it's not going to be meaningful. Our product doesn't phase change in use. And so we're going to back off of that and try to accelerate the oxidation, but not invoke a phase change or some other failure mechanism that's not relevant to the oxidation process that we're interested in. And so that thought process is part and parcel to setting up an accelerated test. Is I'm building into this is that you need to know what the failure mechanism is. Just throwing it in an oven is great if it makes a difference for what you're interested in. Just putting it in the oven and running it for 85 C for 100 hours really doesn't mean anything out of a context of well, what's the failure mechanism? What are you trying to measure? Now, accelerated testing gets really complicated really quick when you have multiple failure mechanisms at play. And so you go to great pains, at least I do, to isolate the failure mechanisms to the extent that I can so that I get a clear method or a clear ability to interpret the results when we're done. But right from the start is what's the mechanism? What are the stresses that excite or accelerate that mechanism? And then how does it relate to the use conditions? And that allows us to set up this basic idea of why applying a bit more stress cheats time. That's the core idea of accelerated testing. So the other piece of this is that we need to figure out if it's failed or not. Now, this really makes us focus on, and it often becomes a discussion of, well, what is a failure, right? So in this product, it's going to be buried in concrete. So a cosmetic defect, a blemish on the jacket, for example, or getting it dirty before it gets into the concrete, it may impact its thermal conductivity a little bit, yet it's not going to overall affect its performance. And so there was great discussion in my case of well, what amount of oxidation which causes it to not generate as much heat over with a lower resistivity value. It creates less heat with the same electricity. So once it's lost 20% of its capability, then it's unable to create enough heat to melt snow. And there's a little bit of a margin in there. So they set this value with doing a lot of experimentation and calculations that if it changes this much, if a light bulb becomes 20% dimmer, we're going to call that a failure. And so this is in a degradation type test. But in other cases, if the on off button fails, but if you bypass that, everything else works, is that a failure or not? If the outer jacket or the outer coating of your product, due to handling, wears the paint off slightly, like my keyboard right now has got some of the characters are missing. It worn off. Um, is that a failure? For me, it's not. I'm a touch typist and I'm not supposed to be looking at the keys anyway, uh, according to my junior high typing teacher. But the idea is that you need to understand, well, what is it you're looking for? If you understand the failure mechanism, you have a pretty good idea what you're looking for. You should. And then how are you going to measure that? Ideally, you do it continuously. Now, there's problems with that. And sometimes the act of making a measurement actually disturbs the stress or the the ability to run the test. You have to take it out and put it at a controlled temperature, for example, and hook up your measurement systems, or your measurement systems don't work, say in a thermal chamber, for example, or whatever stress conditions you're using. There's all kinds of issues around how to monitor it, and oftentimes that's the most interesting or technical aspect of what you're doing. And so it's part of this idea, um, is that you need to know what you're measuring and figure out how to do that. Now, the least effective way, in my opinion, is to wait until you're all done with all the stresses and then pull it out and see if it works and just do pass fail. Now, sometimes that's our only option. And so I call that a avoid it if you can. It's a last resort. So I see a couple of a comment. Somebody lost sound. Sorry about hear that, Paul, and understanding that me saying that probably doesn't help. Um, yeah, and Brian's back, commented on the cost of failures. Yes, totally. It's they can be incredibly expensive. Some are pretty easy and simple to do, yet they change all the time. Let's see. Now I don't get the context, Robert, of what you're talking about with the motor. Uh, so let's see. So if I apply multiple tests, this is a question from Mark, and let's say we get time to failure distributions, various Weibull distributions, four different, say, different failure mechanisms, or even different stresses, maybe related failure mechanism. You got to be really careful in order to combine those results. And I tend to look at it as either a fault tree or a block diagram as a means to put these things together. And one of the underlying assumptions, which goes into fault trees and block diagrams, is that those events, those individual failure mechanisms, are independent. And by that I mean is, let's say you've got one failure mechanism that's due to thermal cycling, but the other one you're interested in is just high temperature. It is temperature related, and so you can accelerate it with high temperature. Well, it turns out solder joints, for example, um, in thermal cycling have a factor as well. What's the high temperature that you cycle it to? And if it gets the higher that highest, the high end of your thermal cycling is, the the it changes the rate at which it's going to fail through a number of cycles. Right? It has an impact of what the acceleration factor is. Likewise, if I'm um, looking at a component that is creating heat, and as it fails, it heats up. The nature of its failure is that it gets hotter and hotter before it finally fails. that can then influence how much heat is available for the other components and other parts of my system. And so sometimes there's a physical interaction between our failure mechanisms and our components within a system. Other times, they're um, that failure mechanisms are interrelated with these various stresses. So you have to be think through the process and the chemistry physics of what's going on such that the the individual failure mechanisms and or stresses are independently influencing the product. So independent of what I do with temperature, the thermal cycling results remain consistent and vice versa. Then you can essentially multiply these things together, combine them appropriately in a block diagram or fault tree. But you have to be careful to check that assumption because if they're interrelated, they may amplify each other or they may moderate each other. You need both conditions in order to get some combined result that's actually going to happen. So it's not trivial. Luckily, most of our products, not all, but many of our products generally have one dominant failure mechanism. And if we can isolate that and work and understand it well, then we're ahead of the game. Uh, Yet there are certainly plenty of exceptions to that idea that we have multiple stresses always acting on our products. And multiple failure mechanisms competing to cause the failure to occur. And so being very clear about that when you both do the testing and when you do the modeling and analysis of that is actually pretty critical. Let's see. Oh, good. Glad to hear that you're back, Paul. Let's see. Sudev, how do you decide the amount of stress that can be applied in an alt when physics of failure is not challenged in normal running cycles? Um, it's a good question, and it's if you understand the failure mechanism, then you can apply an appropriate amount of stress. And the guiding principle here, and I'll talk about it a little bit later in the slide deck, is that you want to apply enough stress to accelerate the failure mechanism that you're interested in. Now, for example, if I'm bending metal, for example, I have a metal rod and the failure mechanism I'm interested in is work hardening or embrittlement. And so if I bend it in an elastic region so that it comes back to its original shape and it just is like a rubber band, it deforms slightly, but it comes back. That's elastic. And but that act can damage the structure of that metal and eventually will lead to its failure. Now, if our application has this, like a bridge, if you're standing on a bridge and a truck goes by, you can feel the vibration and the deflection in the bridge. Or if you see a railroad train going past you, and and I'm sure you've noticed that this iron rail that it's rolling on deflects under the wheels. You can see it deform and deflect underneath the whole rail bed def- drops some perceptible amount. But that metal has to be able to be elastic and return without damage so that the next train can go over it and the next train and the next train. And so as long as it's elastic and it doesn't accumulate damage, it can keep passing trains. But let's say that that deformation was enough that it still returned to its original shape, but it accelerated the amount of micro cracks and deformation and work hardening that occurred within the metal such that it became brittle. And eventually it would break. Now, I'm not saying that you apply enough stress that you bend it so that it stays bent, it deforms it permanently. Now, I'm outside of the elastic region. And at that point, I'm creating a different mechanism, right? So when you think through how much stress to apply, it's not a fixed number. It's not always go up 10% or always 100% or whatever. It's going to depend on how that material or that structure or that system responds to the stresses being applied. Now, if I am using vibration, if I use enough vibration, I can just disassemble the molecules, right? But that's not meaningful to us. That's a different failure mechanism than what it would see in use. And so you want to always apply enough stress that's in between creating an acceleration and it creates the exact same failure mechanism. It manifests the same failure caused by the same root causes as you would see in use conditions. If you can hit those, then you get a range of applied stresses that you can use. And then it becomes what's feasible for you to use, what's possible to use. And so that's a general way to think of it, but it's always dependent on your particular material set, use conditions, failure mechanisms, and so on, and then goes on to other constraints. So great question. We're going to talk some more about this. Um, so create a DOE with each mechanism by itself. Yeah, you can, if you've got the wherewithal, Mark, you can use design of experiments or ANOVA analysis to look for these interdependencies. It's the same or similar concept with that. The issue is that if it's just about everything we deal with is interdependent to some degree at some level, does it make a difference in the results? So if there's a very nominal interference or interaction term, then we can say that the ending results are dominated by the prime, like a DOE study, the factors themselves create the vast majority of the um, leading to the failure to occur. And the interaction term is insignificant. It'll probably always exist to some extent in many of our circumstances, but if it, in some cases, that interaction term can become the dominant factor in and of itself. They have to be both there, like temperature and humidity. If I increase temperature, I have more moisture carrying capability in the air. And so the humidity, even though it's the same number, actually carries more air or more water. And so it's an interactive term between those two things that in some cases is what really matters. Yeah. Okay. And as you know, I'm always happy to take these discussions offline. So just get a hold of me and we'll set up some time to chat for this particular issue on setting the um, for a particular case, which is beyond what we can cover here. The last part of this, the last idea here is really then as you design an accelerated test, there's some key pieces that you need to have in mind when you design the result or design the test and what you're going to measure is, well, how are you going to interpret those results? So let's say everything fails pretty quickly and everything failed with a good failure mechanism, failed the way we expected it to fail. If I apply a lot of stress and I get failures very quickly, I may not have enough spread in the time to failure. Let's say I only monitor my test once a day and I go in and day 4 everything's working, day 5 everything's failed. Well, it's not going to be very difficult for me to get a time to failure distribution from that. All my data is on day 5 and it's just we don't know if it failed right after I last checked it or just before I did check it. So I have this interval of unknown where it actually failed. If only I had done continuous monitoring, maybe I could have by hour or by minute when they actually failed and I get some spread in the data. So you have to think through what happens if that happens. Well, that's bad. Let's do some experimentation to make sure that we don't have a result that happens in between our measurement frequency that makes our data pretty useless at that point. And then on the other case, what happens if nothing fails? is that the design of our test? Or if we're testing to failure and nothing fails and we run out of time, do I have enough information to actually create a result? So think through the worst cases of what can happen, and then how would you interpret it? And then what's the ideal case? So I get some failures on day 2, and then on day 8, and then a couple more out on day 12, and so on. And now I can probably do a Weibull analysis. And I have some evidence that it's a wear out mechanism, for example. So I'm going to do that, or I'll do regression analysis to figure out what's an appropriate one, and so on. But the idea is to think through during the development of your test as to how you're going to interpret it. Likewise, is this a comparison to a goal? See, I didn't know what our customer for this heating cable wanted. I just knew they wanted us to say, here's the probability of it surviving 20 years. And I suspected that was probably a high probability it would do that. And I needed to support if I had an answer of 88% are likely to survive, or 216, or 99.999% are likely to survive. I need evidence to back that up. And so that was my goal. That was my marching deals. And so the interpretation of the results was, I'm using the Arrhenius equation. I have 3 different temperatures. I'm running this test. And here's the assumptions I'm making. I thought through all of that at the start, which then made me have to dive into some statistics and doing regression analysis and modeling using the Arrhenius equation to get acceleration factors. And I didn't have uh, software tools that did all this for me. So we worked it out and used I was using an early version of Mathematica at that time to do it. And so it became part of early on is, what do I need to make sure that I actually measure or gather? What data do I need so that I can interpret the results correctly? And then the other part is, well, how well did I need to do this? Was this like a graduate level study, or PhD thesis type work? No, but it had to be consistent. And my manager at the time pretty much laid out, this is a scientific experiment and you need to do it in your lab notebook, and it's a record that we wanted to present to our customers and back it up with good evidence and good practices. So I couldn't just go into the lab and walk back out and say, yeah, it'll last 20 years. They wanted evidence, samples and appropriate sample sizes and appropriate measurement systems, and making sure that the chambers that say they're at 180 degrees C were actually at 180 degrees C within some range, and so on. So we did a lot of due diligence to make sure that we got it right, so that at the end of the day, we didn't have a lot of doubts about the results. There was still uncertainty, yet we minimized it to the best extent we could right from the start. Right. So let's dive into some other aspects or considerations for accelerated testing. The basic idea is that there's tons of challenges just setting up and running an ALT. The most common is, I need samples. And somebody's going to say, how many samples? And I says, well, I don't know how many samples I need until I know how often they're going to fail and how they fail. Uh, it's kind of this chicken and egg type issue. If I knew exactly the time to failure distributions, I could design a test and tell you I need X number of samples. So I have to make some assumptions, and I have to iterate myself into how many samples I really need in order to answer the question. So part of this is one of the challenges is a key piece in sample size selection is, well, what confidence do you want? Right? What's the probability of a type 1 error that's acceptable for you? And so we often use, a confidence of 95% or 90% or even 80%. And please don't use 50%. You just throw in, bad logic after money at that point, or money after bad logic. Because if you have a 50-50 chance of the results being useful, that means you have a 50% chance the results are not useful. And so it's just flip a coin. It's been my opinion all along. but I digress. So back to sample size, a key part of it is what's your confidence. So my boss initially said, well, I want really high confidence. I want 99% confidence. I went and did some calculations and I said, well, I need 8,216 samples. And he goes, well, that's not, you can't have that many, right? Well, let me show you this relationship. If you want 99% confidence, that's what it's going to take to do this because we're trying to predict the lower tail of this distribution. And if I wanted to know when half of the units failed, then I could do this with, 30 samples, for example. And I'm making up the numbers at this point. I don't remember what the actual calculations were. And he says, well, we're not interested when half fail. That means half these bridges are not working anymore. And that's too expensive. We need to know when the first percent fail or the first 5% fail. So it was iterative of how confident do you need to be? What risk are we going to take that our samples don't represent the population with the statistics of what we're trying to estimate? We're trying to estimate something way out on the lower tail and what would be acceptable to the customer. And so it was a business decision of how many samples, how much resources we need to run the test versus how much risk we're taking and how much risk the customer is willing to take. And so we iterated for quite a while before we got nailed down on some sample sizes. The other piece of this is the general lack of what we do in statistics and in accelerated testing. And then to some extent, in the extrapolation is a part of the statistics. All through my undergraduate study of statistics, it was never extrapolate beyond your data set. So if you measure between 2 and 18, you really don't know how this relationship is going to be when it's 25. That's an extrapolation of some regression and line that's on a chart. It could curve, it could bend, it could go through a phase transition, it just not apply, it could do all kinds of stuff. Your data is from here to here. I'm pointing my hands in front of me. Uh, and if you want to know something that occurs outside of that range, you don't have data for that. Well, we break that all the time in accelerated testing. We say, here's my understanding of its pattern of failure, and I'm going to extrapolate out to the tail. So I know about really well when half will fail of my, say, 100 samples. I know all the way down to roughly the 1 to 2 percentile if I have 100 samples with failures. And but it's pretty vague at that point. I know the middle really well, but I don't know the tail very well. And so if I extrapolate to say half percentile, that's not too bad if I've got lots of samples because I probably have some evidence that helps me in that lower tail. If I only have 5 samples, the ability to create a Weibull curve for that has confidence bounds that are at all meaningful really is pretty difficult down at the lower tails. And so part of the challenge is we need to understand the statistics of what we're dealing with, that the material set varies, but our ability just based on sample sizes also restricts our ability to make estimates. And it also restricts our ability to make extrapolations. And so ALT often uses extrapolation, which then increases our need to get more samples. And because of the variability that occur, that's always there, and we just have to deal with it. And so it's a major challenge to what we do. And it's often not well understood by those that we talk to. This is, well, if I just run 3 samples for a couple 100 hours, isn't that good enough evidence that we're good? Well, maybe. Let's look at the variability. Let's look at what failure mechanism you're dealing with. What do we know about that failure mechanism and modeling and conditions and interaction terms and so on? If we already know all that stuff, why are we doing 3 samples? Why are we even running the test? Which is one of the options that's out there. Now, we always have constraints, and one of them is I mentioned earlier is that we almost never have as many samples as we'd like. And some of that's due to funding or just not enough capability within the lab to set up and run the stuff we want to do. And sometimes our tests, we'd love to do a 9-month study and get really good results, but we need an answer in 6 months. And so we need to take that into account when we design the accelerated life test. Now, of course, there's assumptions. Just about everything we do in statistics and in reliability work has assumptions. And so part of this is that the models and our understanding and all those things of the environment and of the failure mechanisms and so on actually are true, or they're close enough. And the other thing we often assume, and it's worth testing, is are our failure mechanisms independent, right? So if I put 4 units in a chamber and one of them fails, is the nature of that failure, say a power surge, or it emits smoke, or it heats up before it fails, does that influence the rate of failure of the other 3 units that are in that same chamber? At that point, they're not independent anymore. Their failures are being influenced by another one actually failing. Let's see. So let me pause here and ask what's the best ALT. And I saw a question pop up here. Sudev, is there a way I can account for variability in manufacturing while deciding number of samples for alt? Well, it's the the material properties or the dimensions or whatever it is that is important for your failure mechanism is going to vary, right? There's going to be variability in that elements of whatever it is you're making. And if you can measure that, you're going to get a variance term, a standard deviation, and that goes into the sample size calculation. If the variability is very, very tight, right? If the ability of your manufacturing process creates very small compared to the tolerances type of variability, you have an advantage. You don't need as many samples, for example, to know if something is askew or not, or how it affects your product. If they're built nearly identical to each other, you don't need as many samples. Unfortunately, many of our manufacturing processes aren't that precise. And so we have lots of variability. And in that case, we tend to need a lot of samples in order to account for that. Yeah. So Robert, I tend to agree with you. You know what the best halt is? Is not doing a halt. Um, is one way to think of it. Is then you don't have to spend all the money on it, and you have, say, physics of failure data, or you have field data already, or you have other evidence that shows that we don't need to run this test. So if I work pretty hard to not do accelerated life testing because of the duration, the uncertainty, and cost of them. And so if we've got other means to get at this estimate that are good enough, exactly as you're saying here, Robert, that they provide the estimate that we need to make a decision, um, I'd rather not run the test. As much as I love running testing, and setting it up and running and gathering the data, it's not always the best thing to do. The other one is the one where the customer does it for you. I call that the Microsoft model, where you just ship it and let them sort it all out for you and they let you know. Uh, Unfortunately, that's not often a good business practice to let your customers do the sorting out of what works and doesn't work, and then hope you have the time to fix things. Um, the best halt, I agree though with you, Robert, is the one that actually provides you meaningful results that others understand and can use. And that's not always easy to do. Just leave it at that. Okay. Let's see, where's my cursor here? There we go. All right. So I've got a few minutes here. Let me cover a couple different approaches. I did a lot more preamble than I thought I would do, but these are pretty straightforward. So test to pass. Um, It is so bloody common. It's and it's also the least useful approach, in my opinion, except in certain circumstances. If I've got a body of knowledge from my R&D group and we've done a bunch of extensive modeling and testing, and we basically have a really nice physics of failure understanding of our failure mechanism. Um, so if I use that material in a slightly different shape, or I use, just alter it slightly, and I know that if, let's say it's solder joints, and if I went from one dimension of component to a slightly different dimension of component, but I want to make sure that it's okay, and I know that if I run 1,000 thermal cycles on it and it doesn't fail, then I'm good, because it should be very, very similar in performance and behavior and how it fails as our body of knowledge that we already have. Then I'm thinking test to pass is okay. But you can imagine that that's a very tight constraint on it. So if you are got a failure mechanism and you're not really sure what the activation energy is it for this chemical process that leads to the degradation of your product, and you're going to put 20 samples in an oven and monitor them over, say, 6 weeks, and they all pass, they don't fail, what is it you really know? Because you don't have a way to confirm or prove that your assumption of the failure of the activation energy is true or not. You don't have a failure, so you don't know if that applied stress actually was exciting the failure that you're interested in. Um, you don't even know if the oven was turned on, unless you go down and check it, for example. It's kind of a silly example, but it's the idea. The benefit of it, though, is it's often, if you've got enough conditions of it, it's pretty much the simplest one to test. It's often both time and sample size very efficient to allow you to do this. Right. So it has a place, but I've used it exceedingly rarely because it's hard to meet the conditions to when it would be useful. Now, the assumptions are, like most of our modeling, is that the stresses are actually working on the mechanism we're interested in and not on other mechanisms, that we understand how the relationship between our stress and the time to failure model, for example, actually works. We also have to be pretty sure that we're able to detect failures. If we have a very high error rate in detecting a failure, that we're likely to just consider it a pass. And it really applies when there's an intermittent that only occurs at high temperatures. And those that are familiar with HALT know that that often occurs. As you see a failure only at certain conditions, you remove that stress and it works just fine. So if you're going to test a pass and you put it under stress and then take it out and say measure it the next morning, and it might just work, even though it was indicating a failure if you'd measured it earlier or sooner. Some failures are like that, unfortunately. It's one of the hazards of a test to pass. And so, speaking of the risks, is that all too often, and this is one of my pet peeves, people go to the standards, they say, oh, if I put it in 85C at 85 RH for X number of hours and they pass, then it must be good. Well, for what? Based on what? What failure mechanism are you dealing with? The standards rarely talk about where they apply. And just pulling a standard out and saying, well, I'm going to apply that. Well, it doesn't mean it's going to work at 40 degrees C or 20 degrees C for any duration of time or at any RH. It it stresses it. It certainly does. But what? What failure mechanism are you interested in? And so pulling a model out or running a run to pass type test, especially off of standards, is fraught with that it just doesn't apply. And we don't know how to interpret the results. So be very careful in those regards. You can get a number at the end of the day, yet is it useful? I often suggest that it's not useful for any intent and purposes for accelerated testing. All right. Test to failure. Now, it's a benefit because you get failures, right? You get you get the excitement of going off to the failure analysis laboratory and sorting out where the failures we're getting, the ones that we actually want to get, that we expected to get, that they were related to what we're setting up the test for. Now I've got, evidence. I got failures, I got fracture surfaces, I got whatever that I can go take a look at. The test to failure is often time and sample efficient if you have a good model underneath, right? If I understand the failure mechanism and have a decent relationship between the stress and the time to failure interpretation of that, I can run one stress. It's contingent though that I have a good underlying model. If I don't have a good model, then I need to run multiple stresses and create and or verify the accuracy of my model. So in some cases, tested failure is actually pretty good and inefficient. In other cases, you need to do a more thorough and investigative type of a study in order to get there. So it's got benefits in some circumstances, um, but it really is contingent on those underlying assumptions and understanding of your failure mechanism. Again, you got to make sure that the models are good. You can catch the failures that you're doing. The other issue you have is sometimes, and I've run into this, is that um, if I elevate the stress, I excite everything that's excitable by that stress. And I'm interested in failure mechanism A, and it's the one that over the long term that we see in the field, for example, that actually causes field failures. It wears out and it dominates it's the top of our Pareto. So that we're doing some studies to understand what's going on there. And we elevate the stress, but now failure mechanism B has a slightly different response to that stress, and it's much steeper at higher stresses than it is at low stresses. So it now interferes with our ability, it masks the ability to see the failure mechanism of interest. It doesn't mean that it's more prevalent in use conditions, it just has a different acceleration factor. And so some things happen that way where you get masking when you go up to higher stresses. So when you do test a failure, you can check, well, what was the underlying cause of this failure? What was the mechanism here? And you can make sure that you're getting the ones that you want. It's one I've learned this one the hard way is that sometimes failure mechanisms respond to a stress differently. Imagine that. So the idea here is that unless you do a good job of failure analysis, your results may not be all that meaningful, right? And especially if you have multiple stresses at play and or you have stresses that have different failure mechanisms that cause harm or cause scatter in your data for you to understand what's really going on. Okay. So the last one is degradation testing, which is where I started in my career of doing testing in this regard. And one of its great benefits is you don't have to wait for failures, right? So if I have a nice straight degradation pattern following a line saying I'm measuring resistivity, and once it measures 20% of loss of resistivity or change in resistivity, we call it a failure. Um, if I got a nice straight line and I understand that that relationship is linear, I only need a handful of readings to project that line. It's my first extrapolation, and I can project it to failure. So all of my samples uh, will fail by extrapolation. So there's a risk in that, right? I talked about extrapolation earlier, but it allows us to get perfect data. Everything fails. And that has distinct advantages in setting up regression analysis for time to failure distributions. So there's some really cool pieces there. The other part is that oftentimes, because of that feature, we don't need as many samples. And time wise, we don't have to wait until it goes all the way to this change of 20%, for example. Um, I don't, so I can shorten the time that I need to run the test. And so it has some nice benefits. The contingent is that it actually degrades and that it's monotonic, that it degrades and stays degraded, right? It doesn't get better. If you reduce the stress on it, does it heal itself? Well, then degradation testing doesn't hold. So typically you look for accumulated damage over time that leads to that degradation. And in my case, it was oxidation doing chain scissioning in the polymer, which didn't recombine. And so we understood it at that level with help from the chemists in our facility to the polymer chemist that helped me understand that this would fit with this assumption of monotonic degradation. And so many of the other very similar types of assumptions. The risks are is that we're using two sets of extrapolations. First, we extrapolate when it crosses the failure threshold, and we don't have to do that with everything, but we often use that mechanism to get the failure data. And then we use, say, a Weibull distribution to relate stress to time to failure or the distribution, and then we extrapolate out to the tails to the when the early failures start to deal. And I found out firsthand that going through the statistics and the math involved in analyzing this data and the chemistry and the understanding of the phenomena of the failure mechanism was not trivial to explain. And I think I just overwhelmed the customer. And they says, well, that all sounds fancy, but I, okay, we'll believe you. They didn't ask any good questions. So I didn't really know how that went, but they bought it anyway. And, but there's plenty of challenges in doing accelerated life testing. And I've seen dozens and dozens and dozens of them and have had some really interesting challenges in just getting samples or preparing them, isolating failure mechanisms, measuring what we're interested in without altering other aspects of the product, um, and interpreting the results. And so every stage of the way can be um, interesting and something that you can learn from. Let me put it that way. So with that, I think we're just a few seconds over. Sorry about that. Got a few good questions. I wanted to make sure we got to those. Um, I'll stay on the line if there's any questions. And there's a question from Sub planning the number of samples at each stress level. If you're doing 3 stresses, for example, there's a monograph by Meeker, and it's not Escobar. They wrote the book. I think it's in their book also. Um, Meeker and Hahn, I believe, years ago, wrote a monograph where they talked about how do you distribute your samples along your stresses. And you can optimize it. There's all kinds of calculations you can do if you've got pretty good information to optimize exactly how many samples per. But they ended up recommending, and I've seen it in other texts also, is a ratio of 4-1. You put 4 as many samples in the low stress, the lowest stress that you're using, and then 2 samples per, you know, you put 4 in the lowest stress, 2 samples in the medium stress, and 1 in the high stress. And the other caveat is that you need 5 failures per stress level. So 5 at the highest stress, 10 at the medium stress, and what's that? 40 at the low stress. Now, the idea here is twofold. Is one is it weights your test data to the stress level closest to the one that you're going to uh, for your use stress, which you're going to extrapolate using acceleration factors back to. So you weight the overall set of data closest to where you need the results to be extrapolated to. Two is at the lowest stress, it's going to take longer to, if everything is working as it should, it will take longer to get failures. And so you need 5 failures. So if you have 40 of them to start with, you only need 5 of them to fail. Then you have enough data to go forward. And then you have 35 suspensions. And the highest stress, they're going to fail much quicker. So in roughly the same duration, or in my experiences, the high stress tend to fail out pretty quick if you set up a meaningful test. And so I had those 5 failures, the medium stress, like similar logic, right? So it allows you to get enough failures to do the analysis and statistically weights the results where you want the answer to really apply, which is under your use conditions. And so the 4-to-1 ratio is kind of a starting point as you look to optimize your distribution of samples. Oh, good. Thanks. All right. Like I said, you can find way more information out on accendoreliability.com. I know I've written about accelerated testing on and off through the years in various blog posts and so on. You can also find contact information there to me and others that are very familiar with accelerated testing. So always looking for questions. Um, One of my thoughts is to do a series that dive into more depth on accelerated testing and essentially think through and build an accelerated testing course through this process. But let me know if you're interested in that, and I'll keep, excuse me, keep it on the calendar. Um, let's see what else we got going on. Uh, as usual, I'm drawing a complete blank at what I was planning to talk about next webinar. I know Chris Jackson is going to be talking in 2 weeks. He starts at 8 a.m. instead of 9 a.m. Pacific time. So he's an hour earlier, but on Tuesday. And of course, I'm drawing a complete blank and don't have anything open that I can go check real quick. I actually need to write this down. I've been saying this for 5 years, so sorry about that. So, not seeing any other questions come in. I'll let you get on with the rest of your Tuesday or Wednesday if you're in that part of the world. Um, and I'll get the recording posted as soon as I can up on Ascendo Reliability underneath webinars. And so it should be available for you. So now the panic sets in because Zoom doesn't show, at least maybe I don't know where to look, that I'm recording or not. So I hope it recorded. So thanks all. Have a great Tuesday and we'll talk to you later.